Hey everybody, welcome back to Computers and Computations. This week, week 10, we'll be talking about quantum computation. This is certainly an area that's generated a lot of technological interest recently, and we'll talk a little bit about how we can define new complexity classes on the basis of quantum computation, and then we'll leave open some philosophical questions at the end. Okay, good. So let's get into it. So last week we talked about how there were these different complexity classes for different time and space constraints and different models of computation. So we looked a bit at P, NP, and exp. And these model the idea of a problem's hardness, if it's in one of these complexity classes, or the cost required or to solve the problem. How much space or time do you need to solve the problem? So this week we'll look at an idea that can be put to both technological and some philosophical work, the idea of quantum computation. And in particular, we'll see that there's a kind of complexity class that can be defined using this alternative model of computation, much as, for instance, NP was a complexity class defined by looking at a different model of computation, non-deterministic Turing machines, and what they can do in polynomial time. Okay, so I should first identify before I continue that I am not an expert in quantum computing. I do, however, have an interest in how computations might be regarded as more or less feasible. This is something I'm looking at currently, and quantum computation is an example of how a new technology might shift this notion of feasibility, using relatively old ideas. Let's say the idea of quantum computation has been around for a little while, but it's just now things are starting to be implemented, in the real world with real quantum computers. So there's a question of how this might shift that conception of what is feasible if we were to actually be able to build one of these. So I should say that my understanding of quantum computation is not that mature yet, but I'm still interested in seeing how it feeds into this wider question of computational cost for particular problems. So here's the outline of what we'll look at here. I'll first say some brief remarks about quantum mechanics and exactly what kinds of, obviously I won't have time to give a full description of exactly how quantum mechanics work. You could spend a whole course on that. But I'll give the rough idea of the basic properties of the system that we can leverage for quantum computation. And then in section 2, I'll talk about how quantum computation, the rough idea of it, works. In particular, we'll focus on the general notion of a qubit. I think once you've got the idea of a qubit in your mind, it's then a lot easier to address the specifics of how one can build circuits and things like this and actually do some quantum computations. But this initial idea of a qubit can be a little puzzling initially. So we'll mainly talk about qubits in section 2. And in section 3, I'll talk a little bit about how you can define this complexity class BQP. We'll discuss a little bit, but not in very much detail, Shor's algorithm and why that seemed to be significant. And then once I've set those things up, I'll make a few kind of concluding remarks about where we might go philosophically with this. But I think the important thing just for now is just to get clear on exactly what the model we're working with is. Okay, so obviously giving a full exposition of quantum mechanics in under an hour is going to be pretty infeasible. But what we can do is outline the core features of quantum mechanics that are going to be relevant for quantum computing. In particular, what are the properties that we're going to leverage when it comes to uh, defining what qubits are and then using the properties of these qubits to get speed up for particular kinds of problem or possible speed up. Okay, so we should note that quantum mechanics is both very well understood in the sense that we have very precise calculation procedures for quantum mechanics, very mathematically well understood. And we can really make very, very good predictions on the basis of quantum mechanics, up to really absurd levels of accuracy. In some senses, possibly the best confirmed scientific theory we've had. But at the same time, the kind of foundations of quantum mechanics are really poorly understood. There are many interpretations that have been proposed for what the physical meaning of these quantum mechanical theories are, how we should understand the relevant properties like superposition that we'll discuss shortly, but there's no one interpretation that clearly stands out as the best, let's say. So it's both simultaneously a very clean theory, but also the intuition surrounding it can be really, really difficult, and it's created a lot of philosophical controversy. So we need to be careful not to prejudice our understanding of quantum computing by relying on one or other interpretation of quantum mechanics, though, as we'll leave open later, maybe you think that certain interpretations for quantum mechanics are actually suggested by the behavior of certain quantum computational algorithms. This is something that David Deutsch has proposed. But the core starting point for quantum mechanics, at least from my perspective, is that our standard reasoning about probabilities fails when we're dealing with quantum phenomena. So we have a sort of very good mathematical theory of probability, how these should interact with one another. But this kind of classical, well-understood mathematical theory of probability just doesn't work when we apply it to quantum mechanics. So Bell-type theorems are an example of this kind of phenomenon. If you've heard of them, but I'm just going to present a really kind of simple example and leave the rest for your own research. Okay, to make this point, we'll consider an example from David Albert's Quantum Mechanics and Experience. And what we're going to do is we're going to talk about two properties of electrons. I'm going to call them color and hardness, but this is basically euphemisms for spin properties. Right? So every electron is either going to be black or white or hard and soft when measured, right? So I have an electron, right? And it comes in, I make a measurement, right? And either it's hard, right? Or it's soft if I test for that. Or if I'm testing for color, it's either black, right? Or it's white, right? And those are the only options for these two properties of color and hardness. Okay, secondly, the two properties are independent, in the sense that we've never observed any kind of correlation between hardness, softness, blackness, or whiteness. So it's not like all the hard ones are white or something like that, or all the soft ones are black, or there's any kind of probabilistic relationships between them. Moreover, if we repeatedly test the same electron, we get the same result. So I've got two boxes here. This is how we'll draw the diagrams for the things that we're testing the electrons. So electrons come in here, right? And if it's black, it comes out this arrow, and if it's white, it comes out this arrow. And if it's hard, it comes out this arrow, and if it's soft, it comes out this arrow if I send it into a hardness box, okay? So normally, whenever we send just a bunch of electrons with nothing else having been already done to them into a color box, it comes out 50% black and 50% white, and for hardness, 50% hard, 50% soft, okay? But also if we test the same electron over and over again, it will have the same property. So if I send it into a color box and it's white, and then it goes into another color box, it will come out white again. So let's just look at one surprising result we get about the behavior of electrons, right? Given these kind of measurements. Okay, so we're going to do three things. First, we're going to isolate a bunch of electrons that are white. So I send a bunch of electrons in here, and I just focus on the ones that come out as white. Okay. Now, so this is taking this bit here. I've isolated all the ones that are white, and I'm now going to measure them for their hardness. So I send this into a hardness box. Okay. So all these white electrons are going to this hardness box, and as we would expect, since there's no correlation between whiteness and hardness or softness, 50% come out hard and 50% come out soft. Okay. Now, what I'm going to do is I'm going to, for either one of these two beams here, I'm going to check their color again, right? So we've isolated the white ones, we've checked whether they're hard or soft, and now I'm going to check their color again. Okay, so what happens? Have your guesses now. What happens is that 50% turn out to be black and 50% turn out to be white. And this is, incredibly surprising because we thought we had isolated all the white ones. So there is something very strange going on when we measure them for hardness that somehow disrupts the color of the electrons. Now, there's many more other kinds of examples, and many get more and more problematic, but this is going to motivate the rough idea that something needs to be changed about ordinary conceptions of probability. Because if you think that 100% of what we sent in here was white, and there shouldn't be any relation between hardness and softness and whiteness, you should expect 100% of stuff to come out here. But it seems that our normal ideas about probability are being affected by what goes on when we measure a box. We measure these things using hardness and softness. And this is going to in turn be something that we're going to leverage, this idea that these kind of measurements can interfere with one another, these states, when we come to talk about quantum computation. Okay, good. Now there's lots of examples of this flavor, and some of them can push the point a little harder that probability needs to be modified somehow. But this is at least a nice easy example, and the way quantum mechanics deals with these kind of problems of probability is you have three interacting kind of parts of quantum mechanics. So first you have like a generalization of the laws of probability to allow probabilities to have complex values. Okay, so if, for instance, if I talk to you about like a minus 20% chance of rain, right, that's not going to make any sense, right, normally, but we're going to work in a context in which that kind of thing can be said, but we're working with a framework in which we just acknowledge that there can be these things called amplitudes, and these are the kinds of things that can have negative values. So the second thing we're going to do is we're going to allow particles to be in linear combinations or superpositions of states like hard and soft. Okay, so I have some electron and it can be hard, it can be soft, or it can be in some superposition of hard and soft, and that can be lots of different linear combinations. And you can sort of think of it a little bit like the probability that when measured it will get the result hard or soft, right? So it's not but it's probability in inverted commas as well. It's probability in the sense of these kinds of amplitudes. Now, the interaction of these amplitudes, so this is 1 and 2, is going to allow particular kinds of interference and also particular kinds of amplitudes cancelling each other out. So if I can have a negative amplitude as well as a positive amplitude, this is going to allow them to cancel each other out in a way that one can't do if one's summing probabilities, for instance. Okay, so there's a couple of things to remark here. I mean, firstly, this is all really baffling, right? These idea of amplitudes, what really are they? One might want to ask, what really is it to be in a superposition of different states? And this is the place where those are questions one can ask from a kind of foundations of quantum mechanics standpoint, but that requires you to then start talking about interpretations of quantum mechanics. For the purposes of what we'll look at here for now, really, these are just the concepts that work. So what is an amplitude? It's going to be the kind of thing that can play this probabilistic role. It's really a perfectly good mathematical entity, even if its kind of physical meaning is a bit unclear. And what is a superposition? To be in a superposition of different states? Well, this is just, something that is mathematically defined and that makes very good predictions about the way the world behaves. So I think there's a sort of potentially an analogy here between if you had never encountered gravity before, let's say, or the idea of gravity, let's say you just thought God made sure that everything stuck to the earth. And then Newton comes along and explains to you that between any two masses, there's a particular attracting force on the basis of their mass. You might say, well, what is gravity really? I don't feel the gravity between myself and the cup that's currently on my desk, for instance. What exactly is a force? And I think in that position you might want to say something like, look, this is just at this stage just a fundamental thing about the world we observe, right? You might want to say that to the interlocutor, and it allows you to make all these wonderful predictions. We're in a similar position now. We don't really understand what superposition is, but the mathematical framework in which it occurs allows us to make lots of very, very, very good mathematical predictions. Okay, so that's a very, very, very rough outline of the kind of phenomena and kind of concepts we're dealing with in quantum mechanics. Let's talk about quantum computation and roughly what how that is able to leverage these features of quantum mechanics in order to get desirable outcomes. So what quantum computing uses is it leverages two facts about quantum mechanics in order to get speed up over classical algorithms for particular problems. So the first thing to note is that there is a lot of information encodable within these superpositions. So any linear combination, right, is going to be of states is going to be a superposition, and this is going to give you, huge amount of possible states that these particles can be in, right? You might have or you might have only a couple of states for a classical computer. Let's say a bit for a classical computer. What we're going to do is we're going to use that there are so many different states a particle can be in to encode a lot of information into what will be the qubit. And secondly, because you have interference between, or you have the possibility that amplitudes will do things like cancel each other out, and you also have interference patterns between different particles. What we're going to do, and we'll see this a bit with Shor's algorithm, which I'll give a very coarse description of later, is you set up some kind of nice inference pattern, and you make sure it has enough similarity to other other mathematical problems or computational problem you want to solve, and then you use the properties of how the interference is going to go down when you make an observation to infer with high probability that such and such an outcome might happen. So these are the two kind of critical things. You have a lot of information encoded into superpositions or a lot of possible states, and you have the ability to make these states interfere with one another. Okay, good. Let's talk about what a qubit is. So a qubit is just some quantum particle. And this could be a photon, they could be made of photons, they could be ions. There's lots of kind of concrete choices one could make for how you actually implement a qubit or engineer a qubit. What we'll do is we'll talk about qubits at a very abstract level, and then there are different ways those can be then constructed. And this is no different from classical computation, right? We talk about bits, zeros or ones, but there are lots of ways that could be implemented. Transistors, old school vacuum tubes. It's a similar kind of principle we're discussing at this stage, the kind of theory of what quantum computation or what qubits are. Okay, and what's going to happen is when I measure the qubit, right, just like with our hard and soft electrons, right, we're going to get a 0 or a 1. We're going to get one of two definite states. But importantly, if I do the right things, I can also prepare the qubit, or as during a computation, a qubit can also be in a superposition of states. So this would be like for instance, I could prepare a bunch of white electrons to be in a superposition of black and white by sending them into a hardness detecting machine, right? So what we end up with is a qubit can be represented by this thing called the Bloch sphere, okay? And so we have a top element, this is our kind of 0, and then we have a bottom, right? This is our 1, or I mean, it doesn't matter which is top and which is bottom. And this is a three-dimensional sphere, and then there'll be a whole bunch of superpositions of different states, and a particular superposition is going to correspond to, we're thinking of these things as particular states as vectors, and some superposition is going to correspond to some point within this sphere. Okay, so you see how there are a huge number of possible states for a qubit, right? So we have the standard kind of 0 and 1 that we get on measurement, but we also, we can have different points in the sphere being states for the qubit, as long as we prep them to get the right kind of superposition. Okay, so what you can kind of intuition that's helpful here is that the position on the sphere, right, or in the sphere, is going to affect the probability that you get a particular output, right? So if I am in this position on the block sphere, for instance, it's possible that when measured, that this little guy goes down to becomes a 1, but it's much more likely that it snaps up and becomes a 0 when it's measured. Okay, so this is what we're going to use a bit later when we look at making measurements in order to get desirable outcomes for computations. Good. Now, one can then define quantum gates, much as one designs circuit gates for classical computing, that are universal in that you can show that quantum computation allows you to compute any computable function using these quantum gates. So what we then do is we prepare states for inputs so that the chance of the corresponding circuits outputting a 1 is very high if the inputs are true for some desirable problem. Okay, now I won't talk about quantum gates, they're a little complicated here. There's plenty of resources, you can read up on them. But the idea is that we have some bunch of circuits, right? And I'm going to prepare some states, they're going to be input. And then what I'm going to ensure is that if I get a 1 here, I can be pretty sure that this input had some particular property or other, depending on exactly what the nature of these circuits are and how I defined what circuits I put into it. So this is the sense in which, and we'll see a little bit of this when we talk about the complexity class, this is kind of where the work is, in a sense, is to set up these circuits in such a way that given the requisite kind of states, they'll do the right kinds of operations on those states, such that when I make my final measurement and collapse a bunch of stuff, I get with high probability 1 if the answer was yes to the problem I set up. Okay, good. So that's a very rough description of how qubits can be fed into quantum circuits and how this can be used to solve particular kinds of problems. And you can, as long as you set up the circuits well, then you can, compute various kinds of problem. Okay, but we can also, interestingly, from the point of view of feasibility, define new complexity classes on the basis of these kind of tools. So bounded error quantum polynomial time, or BQP, is the class of all languages for which there is a uniform family of polynomial size quantum circuits. Okay, what does this mean? This means that I can define a classical algorithm, right? Classical computer that will define this family of circuits for me in polynomial time, right? So I can set up my circuits C0 to Cn, right, using a classical computer to set up these set up the circuit before I then feed in my quantum input, right? Okay, when do these things accept and reject? Well, we say that the input it holds for the particular input. If for x is in this particular language, then Cn accepts with at least probability 2/3, and it's not in there. If it's not in there, sorry, then it will only accept 1/3 of the time. So most of the time is the core idea. Your circuit is going to output a 1, right? So just to make a quick remark about the place of BQP in the kind of complexity zoo, we know that BQP is, every problem in BQP is also in P-space. Every problem in P is in BQP, and it's unknown what the relationship between BQP and NP is. So let's just talk a little bit about kind of technological implications of quantum computation. So critical for the standard cryptography that we use is many of the problems associated with this kind of standard kind of cryptography is the problem of finding the prime factors for some large n. If you can do that efficiently, then you can break a lot of cryptography, right? And this was part of the reason why P, whether or not P is equal to NP, is a really interesting problem, because we know that this problem is in NP. It's actually suspected to not be NP complete, but the problem itself is in NP. Now, if P was equal to NP, then I would be able to solve this problem using some polynomial time algorithm and break all the cryptography. Now, what's interesting about BQP, and in particular something called Shor's algorithm. So Shor's algorithm, very roughly speaking, sets up the superpositions for the relevant circuits in such a way that for a particular factoring problem, there are kind of collapses that are bad, and there are collapses, that will give you the wrong answer for the factoring problem, but these cancel out. These different collapses have amplitudes that interact in such a way that you're actually able to factor n with very large n with high probability, and just really importantly do so in polynomial time. And factoring is for on the grounds of Shor's algorithm is in BQP. So if one of these things could be built, you have the resources to break all known current cryptography. This is interesting because, non-deterministic Turing machines, it's very unclear what a kind of physical model for those might be. It's very unclear, that I could build a sort of meaningful non-deterministic Turing machine and use an NP algorithm to break cryptography, but this is very possibly physically realizable. So this is the interest of quantum computing at this stage, or at least one of the interests, is that this is a problem for which we only have bad algorithms for using classical computers or slow algorithms, but we have a very good one for quantum computers. Just before we close, I did want to address one question that occurred when I was first thinking about this, and then I realized was actually not so much of a problem, which isn't classical computing just way better than quantum computation, or at least in one respect, because Turing machines have a 100% chance of working, in the sense that they will give us a 1 in virtue of the fact that they're completely deterministic exactly when the relevant computable problem is, the relevant input is a member of the relevant computable set, and a 0 when it's not in the relevant computable set. Okay, so they're deterministic things. They have 100% chance of working. So is this not an advantage of the classical model? Okay, well, yes, but not in practice, assuming that we could actually build a reasonable quantum computer, or a scalable one. The reason being, they are different in this sense, abstractly speaking, but in practice, an actually instantiated classical computer can also have failures, right? Transistors can fail. These are not perfect, even if the very rarefied Turing machines are perfect operators. So yes, the Turing machine model as a mathematical model is sort of 100% reliable, whereas BQP, even as a mathematical model, is not 100% reliable. But practically speaking, if you ever wanted to implement these things, there would be very little significant difference other than the usual engineering issues associated with quantum computation. I mean, note also that even if you only think, oh, I only get a 2/3 accurate answer, you can just also repeat the algorithm over and over again. So if you want more up to any desired level of probability, you just have to repeat the computation to get more and more higher probability of the answer being yes when it actually is yes. Interestingly, there is a kind of computation or complexity class that factors in this kind of issue, and this is called BPP, and this is, allows for there only being a certain probability that we go to a particular state. Good. So that's just to say that this is a very sensible question to ask. It's true that they're different mathematically speaking, but in terms of things we could actually build, potentially, they are not so different abstractly. Okay, so I just want to conclude with a few philosophical remarks and talk a little bit about what we might think the implications of quantum computation are, or at least what has to be done in order to draw philosophical conclusions from them. I would say that I don't fully understand the implications of quantum computation for philosophy. And part of what I think is going on here is that it's not clear to me exactly what the explanatory challenges are. So let's talk a little bit about that. I mean, quantum computation is certainly a technologically, very enticing kind of technology. It might be that we can break a lot of current cryptography protocols using it. It has been put to philosophical work in a variety of contexts. And I think one of the most famous ones is David Deutsch's argument that quantum computation supports the many worlds interpretation. Okay, so this is the idea that when I make a particular measurement, there are genuinely two kind of real worlds that exist. Okay, now something that David Deutsch claims is that the only way you can make sense of these kind of algorithms working is that the number has to be factored somewhere. So it has to be factored across all these possible different worlds we might we might get. The information has to be being computed there somehow. This seems to be roughly his argument, although I confess I don't completely follow it. However, I find this a really strange kind of claim to make, because part of what you're doing with a quantum computing algorithm is you're exploiting the interference between different qubits, for instance, and different kind of possibilities for collapse. So it's really unclear to me if the many worlds interpretation can actually support the kind of interferences required to really explain how the algorithms work in a different sense, even if it is the case that there's enough information for the many worlds interpretation. So it's unclear to me exactly what the explanatory challenges are, and I don't want to claim that that's too serious an objection to Deutsch's argument. I guess it's more a question for me to think about as I look at this issue a bit more.